Dear folks, it's 7 o'clock. We're going to get started. Thank you so very, very much for being here for Ocean Voices, where we get to learn from the expertise of those who listen to the whales. I'm Jackie Hildering. I'm a co-founder for the Marine Education and Research Society. I am a humpback researcher, and as the education and communications person, spend a lot of time flapping my lips. So that's what I'll be doing tonight as the host for this event. Marika will be talking to you briefly around some of the technical aspects. In case you have any problems, she's our go-to. We will do a round of introductions of those whose faces you can see, our dear panelists, and then I'll provide a bit of background on this project. We are sharing 2 animations never seen publicly before. The first one will be shown, then we'll have 3 presentations from our experts, show you the second presentation, and then have a round of any sort of questions left at the end. I'll hand it off now to my colleague Marika, who will talk about the technical pieces of the webinar.
Hi, folks. I just want to draw all of your attention to the Q&A function. If you want to ask a question for any of our panelists at the end of their presentations, we might be able to answer them. Please do pop any questions in there. You may have noticed that chat has been disabled. So if you do have a question that you would like answered, please pop them in there. Also, if you're having any technical difficulties, I can get back to you if you use the Q&A function.
Okay, we're going to do a quick round of introductions for the other faces that you see. Marika and I are Team MERS. I think we'll get the most tired person on this call potentially to be the first one who waves and says hello and who she is, because in her time zone, it's 3 a.m. Go.
Hi.
Dawn is the animator for the 2 animations that you'll see and has done so much good in helping us with education in the Marine Education and Research Society, but indeed has just arrived in England and it's 3 a.m. There. Then in order here of the presenters, if people want to say hello and who they are, Helena?
Sure, I'm Helena Symonds. I'm a co-founder of OrcaLab, and I live on Hansen Island.
Hello, everybody. My name is Ben Hendricks. I'm from SoundSpace Analytics, and I specialize in software to process and visualize ocean acoustic data that will be seen today.
Thank you, Ben. Harald, that's you. Oh man, we lost him.
Oh no.
Valeria, do you want to go?
Sure. Hi, everybody. So glad to be here. I'm Valeria Vergara, and I'm a marine mammal research scientist specializing in animal communication, whale communication, and impacts of noise. And I co-direct the cetacean conservation research program at Raincoast Conservation Foundation.
And last but not least, Dr. Yurk.
Yes, I can't see you right now, but I hope you can hear me.
Yes, you can.
So yeah, my name is Harald Yurk. I am a physical scientist with Fisheries and Oceans Canada. My main area is whale detection right now, but I also worked before as somebody who looked at noise impact assessment, and I still do a lot of that work for DFO right now. And I will be talking to you, I will give you a little bit of an insight into the physical acoustics world tonight. Well, maybe for my background, I used to do killer whale sound research. I did work mostly with Alaskan killer whales, but I also did some work in BC as well. Okay.
Thank you so much. Okay, so what the heck is this Ocean Voices thing? So as educators who have a background in whale watching in the Marine Education and Research Society, I think it took a long time for me personally to find my way back to understanding just how powerful it is for people to understand that marine mammals live in a world of noise. Our experience on whale watching boats, when we would want guests to be able to understand the privilege of what they were seeing and why we had the engine off, we put the hydrophone in, and independent of language barriers, people would gasp when they got a chance to hear the whales. So we found our way back where what we hope is that if people understand the ocean as a sound trap, there's a world of whales there and so much more, and how we're impacting that, that would mean, hopefully, that it would compel compliance and understanding. That instead of the focus being on, you have to stay 200 meters away, 400 meters away, what are the whales doing? What area am I in? That the hope is that in understanding the noise that we're making and how that has an impact, that would make people want to do the right thing, and do the right thing by way of what you do as a boater. And that is everything from distances and speed limits to potentially no-go zones and avoidance zones, that is in supporting quieter technologies, and that is also in what we do as consumers and voters, in what we support, in where things come from and the fossil fuels that we use. So this led us to applying to the North Island Marine Mammal Stewardship Association and their conservation fund. They funded this project, for which we're very, very grateful. We had in our sights the animations that we wanted to do that are incredibly reliant on what OrcaLab does. Our neighbors, who are the ones who have for years and years, and very thankfully you'll be hearing about that, who have been doing exactly that, allowing people a window into the acoustic world of the whales. So based on 2 of their recordings and Dawn's handiwork as an animator, we came up with 2 animations. We wanted a website very solid in science to support those animations. We are not the scientists, so we asked some lovely humans to please share their expertise with us, and they have done so, for which we're very, very grateful. And then all of this will be incorporated into an online boater course that we're developing, especially the animations. If you go to the website, you'll notice it's very dense right now for text. There's all kinds of interactive elements that will be being added to the website. But that's the background on Ocean Voices. And we may be the catalyst. It's funded by NIMSA, but it's the people who are on this call who have truly made it possible. And it's very, very heartening to see your interest. So here we go. You ready for this, folks? It's a big deal for us. Here's the first of those 2 animations. The vocals, the recording is thanks to OrcaLab, the animation by Dawn. Whales live in a world of underwater sound. They depend on sound to communicate, to find food, to stay in contact, to navigate, to socialize, to choose mates. Sound is magnified in water. Boat by boat, we add to the whale's stress. And there can be no better transition than handing it off to Helena Symonds.
Hi. And just 1 second. I just have to preface this that we are at OrcaLab because it's incredibly foggy outside. We're experiencing some problems with the internet. I really hope goes well, and I'll start, and maybe Jackie, you can.
I'm afraid we may have lost you, Helena. Anybody spot the irony? The excellent communicators, those who study sound. We will get Helena back. We're all nimble here. Ben, how do you feel about talking about the technology side of things in the hopes that we get Helena back with a more solid internet connection?
That's right. Yeah, I'll start with this. And if we find Helena is popping back in, we'll just switch over. I think that would make most sense. What I think Helena mentioned already in the part that has been communicated to us initially is that sound is really important for marine mammals and whales in particular to make a living in the ocean. And I think what Harald and Valeria later will emphasize as well is that how sound or noise can be a threat to these same animals. So the section that I will fill, I want to highlight that sound, for the same reason, has also a special importance to the scientists because it's our preferred tool to study whales and the ocean in general. So maybe if you consider the ocean to be a living organism, which it actually is in many ways, and us being doctors, which most of us aren't, then hydrophones are kind of our medical tools like X-rays or MRI or a stethoscope, which we can use to monitor the vital signs of the ocean. And the tool that I'll be talking about is called CStats. It's a web-based dashboard that really has a single outstanding goal in mind, and that is to make the vital signs of the ocean visible instantly to everybody and everywhere. And I don't really have a PowerPoint presentation, as you can see. This is no glitch. I think my way to go is I just share my web browser with you and walk you through the website that hosts these dashboards, and then the dashboards itself, and there you can learn how the scientists try to use sound to read these vital signs. So the page that you're hopefully all seeing here, maybe I get a thumbs up from the crew. This is visible. It is. The page that you see here has just been launched today. It's actually a big day. It's from the BC Hydrophone Network called whalesound.ca. Everyone, please not going on there right now, but after the talk here, it's been live since this morning, and it features an interactive map, which I'll be clicking on right now. And you can see a map of BC. And some of these places have symbols that indicate hydrophones in the water. Here's a list with all the sites that actually have a hydrophone and that currently measure ocean sound and its metrics. And I'll go on one of the sites that is located at OrcaLab, where Helena is with her poor internet connection, which is called Flower Island. You can see it zooming in, and from this website, from the map, you can access the dashboard to interact with these ocean data that comes out of the water. And instead of going through the website, I'll just pop up the dashboard itself in a separate tab. So this is the dashboard from Flower Island. You can see this is the OrcaLab logo. Maybe you recognize the lab that Helena mentioned. The site's called Flower Island. The other thing you recognize is that the data in here has been updated just 17 hours ago. And the status, woohoo, is online. So the hydrophone is actually in a better way of communication than Helena herself. How is this possible? You'll ask. How do we have this information available from just yesterday, pretty much? And the reason for that is that the dashboard itself is driven by automated software. And more particularly, it's AI-driven automated software that communicates with the hydrophone and the dashboard to make the data flow directly kind of from the ocean into the internet, being available to everybody within minutes if we want. And right now we typically update this information per day. The other thing you can already pick up on this landing page is, oh, we had acoustic activity. The latest acoustic event was humpback vocalizations, of which we detected 71 calls on October 7 in the evening. So pretty much 2 days ago, there was humpback activity. And knowing OrcaLab and seeing what is going on, this is probably actually humpback song going on right now there. And if we start to explore the different options that the dashboard offers, I try to walk you through how you can read the soundscape and what you can interpret from the data we collect. So let's dive into the daily detections, which is a pretty easy to understand metric, because what you see is how many whale calls we detect on that site per day. And I'll just unclick the humpbacks actually to focus on the orcas. And each line here is for a calendar day, and you start to understand, okay, when do we have activity? Apparently a lot end of August and beginning of September. You can hover over each of these days, and for example, you can see, oh, April 13th. Oops, I have to find it here. About 120 calls during that day happening. And you can dive into a second metric, which is called a bubble plot, or that's how I call it, and see how exactly that actually happened during that day. So this plot here is not just telling you how many calls per day, but it tells you when in the day this happened. So you see this here, this is the time of the year. You can see a calendar year or a little bit more. I can zoom this out. This is exactly our 2023. And this is the time of the day. Here's our nighttime. This is our daytime. And on April 13th, this is our little event that we just saw on the other plot. So we recognize it happened in the middle of the night between 1 and 2 in the morning. About 100 calls were detected there for Orca alone. And yes, you can see that later on, there was more events around the end of August and beginning of September. And all these little red dots are the humpbacks who just started to become active and start singing there. And this metric can be explored either for a year, or we can go back further in time. If I go back the full 3 years that we monitored, you can see these patterns of activity. Just looking at humpbacks, they really pop in at a specific time of year, are very vocally active, mostly during the night, and then they disappear vocally. And this seemed to be happening year after year. Similar for the orcas with a different pattern, but also at very specific times of the year. Now, if we keep with this event that we just saw in the middle of April here, let's have a look at the full day of soundscape that was recorded. This is a metric that we call spectral averages. And what you see is the full day of acoustic activity that was going on in the ocean, everything that was recorded on the hydrophone. Oop, that's the wrong month. Here we go, April 13th. So how do you read that plot? First, you can see on the bottom, you can see the time of the day. So from midnight to 24 hours. And then on this axis is a weird looking number, and that is the frequency that has been recorded. Frequency is how low or how high the sound is that we recorded. And the color shows how noisy it was. So anything in yellow means it was loud. Anything in blue or black means it was quiet. So the features that may be most prominent are those kind of vertical lines zipping through here. And each of these lines is a vessel passing the hydrophone. So for a time, it just insonifies the whole soundscape. It's very noisy. Everything disappears behind it. And then eventually the vessel is gone. So just by counting these things, you recognize on that day how many vessels have gone through, which looks like it's maybe around 20 or 25. Now, if you zoom in and you're careful, you can see other things. And this here, these little speckles, is our orca vocalization. So you can see they're not very loud as compared to the vessels, but they're in here and we can detect them. Other features are rain, which is the very high frequency noise you can see up here. And then these areas who are just blurred in noise, this is probably wind and waves that have been going on that day. And the same thing, I could just check how the most recent observation was, which was the 3rd of October yesterday. And what do we see? We see the vessels, of course. You can see a pattern in that there's some few vessels in this time and then a lot of vessels here, which is the day-night pattern, where during the day there's more of these small sipping recreational vessels, and the big ones here are probably either ferries or cruise ships or barges going through. So these daily soundscape plots are really nice to exploit what is going on at these sites. And the last metric I'll just pop you in before I give it back to Jackie to see if Helena made her way back, is the sound levels, which is another word for noise. So this plot here shows for that hydrophone site the daily noise levels, and I can select a specific frequency band I'm interested in. But more general, I can just see the trends and pattern that are going on with more noisy and less noisy day. I can smooth it out to get a broader picture of the season. And what stands out to me is this peak here. Looks like it's been, I don't know if it's quiet or not, but it's been at a certain number for most of the year, and then it spikes up by almost 10 decibels in the middle of the summer. So this could be weather related. Storms and wind and waves create higher noise levels, but because it happens in the middle of the summer, I would suspect this is because of boating. And as an ocean doctor, I would say this is maybe a concern sign where my ocean vital signs are in trouble, and I better have a look at this and see if this is okay. Okay, so I'm moving back to the summary here just to wrap it up. To maybe before going back to Jackie, to highlight that the dashboard itself is always a work in progress. We'll always look at feedback and see what people need. We'll wait on the newest research developments, and then we hopefully being able to implement new features that help people more and easier understand these ocean vital signs. And something that you can look forward to in the next year, for example, is a map where we will start localizing and tracking whales, and these tracks and localizations will be visible in the dashboard as well. All right, Jackie, how are we doing?
Yeah, I think many minds were blown. Thank you very much, Ben. That's incredible. We don't have Helena back, but she's trying to get me her presentation, and we'll slot her in later. That was incredible. We'll do 3 short, quick questions. We're not ignoring the other questions if we're not answering those now, folks. It's just that I know what's coming, and those questions might be better placed later on. So some very quick questions, Ben, for you are the name of the technology. I'm assuming that is whalesound.ca that's being asked. That was a question by Alexandra.
Yeah, so to get the final product or the final knowledge visible in the internet, it's kind of a multi-step process. First, there's the technology to actually have the hydrophones in the water, which is big and sometimes very difficult in remote places to achieve. Then as the next step, there's the software that uses AI to process that data and generates that information. And then we need the web platform that hosts that information. And this is whalesound.ca, which is the umbrella for a lot of organizations partnering up along the coast to make their data visible together. And then CStats is the specific tool where you can interact with that data. So it's these multiple steps working together, and that shows how difficult it is to get to that point, and how happy we are that the website will launch today.
Yeah, incredible. And so grateful that that's the timing as well. A question from Darla is, are you able to determine how many different animals there are amongst the calls?
Yes, that's a good question. The software doesn't do it. In that respect, the humans are still way better. If Helena would be on the call, she would tell you that as soon as they hear whales, they know which family or pod it is. And because they have such incredible historical knowledge, they know how many animals live in these pods and families. And then they already pretty much know who's around and who's vocal. With humpbacks,
Yeah.
oh yeah.
Those darn humpbacks, though.
Yes, with humpbacks, we just assume they're singing by themselves, which is, I think, a good first assumption, but not always true, maybe.
And then one more question before we move on to Valeria is from Jill. Ben, is it possible to visually overlay the spectral averages onto the acoustic events?
Yes, well, I think the next step that we try to get to is to not overlay a spectral average image to the events, but to overlay the sound to the events. So ideally, people in the future will be able to not just see presence and activity, but they can actually listen to these events and match those with a specific recording. But adding the visual spectrogram to that shouldn't be impossible. So stay tuned.
Okay, wonderful. I think what we'll do, I do have Helena's presentation, which is brilliant. But now we need a Helena. So I think we'll move ahead. Oh, wait, we have a Helena. Okay, wait, this will work. So Valeria, you're on standby again. We're going with Helena. And I am sharing my screen, and Helena, very likely you want to lose your video, and it's all going to work amazingly, folks. Here we go. Here we go, Harald, you're on. The physics of sound.
It's sort of frozen, which is not what I want.
I love the irony that Ben's just shown us like the most amazing technological advancements. You're good.
So good. So yeah, I will talk to you a little bit about the sort of I'm not a physicist. Actually, Ben should really do this. You know, he's the physicist. But no, I'm talking about a little bit about the physical background of underwater sound. Telling you a little bit about why it is important maybe to animals, and then also a little bit more why noise has the impact that we think it has. To start out, I jumped into physics. It's sound is pressure, and as Ben already mentioned, he had a little metric there and how pressure is measured for sound. But the top diagram here shows you how the pressure is actually asserted into the water and how it's actually traveled through the water. It's a compression wave going through the water, and you can see the water gets compressed and then it releases, and then compressed and releases depending on what the noise source does or the sound source does. And because the energy doesn't dissipate completely, it starts propagating in the direction that the push came from. So you see that comes from the top left and then goes to the bottom right. And you also see that certain parts of the water column gets compressed, and then certain parts are relaxed afterwards again. And that is shown in the bottom right one, where you see the different wave fronts of that pressure wave going through the water from the noise source at the left to radiating out towards, in this case, towards the right. And the two metrics that are important for us are the wavelengths, which is sort of the distance between the two wave fronts, and the frequency, which also Ben mentioned is very important because it gives us the pitch. The frequency is the number of wave fronts that we have per second going through a certain point. To give you sort of a little bit of an illustration of what that is, I will play you two sounds. One has a longer wavelength and is therefore a lower frequency, and one has the shorter wavelengths and has a higher frequency. Play the lower frequency first. I'm sure, hopefully you all heard that. And now the higher one. So you can hear the pitch is quite different, and that's what makes us characterizing a sound. But what is important for the propagation, so for the traveling of the sound through the water, is when you look at the longer wavelengths and the lower frequency, it has fewer interactions with the water column than, for example, the higher frequency, which has much more oscillations and interacts with the water more often. So what does that practically mean? The lower frequency dissipates less over distance than the higher frequency. And that's why, for example, lower frequency sound travel much, much further than the higher frequencies. And that's, of course, important because animals that use lower frequencies, like, for example, blue whales and fin whales, try to communicate over much, much greater distances than, for example, hover porpoises, which use really, really high frequencies. And unfortunately, also, some of the noise sources that we put into the water are also low frequency sounds. And so they travel very far as well, especially ship sound. The third part that is beside the frequency and the wavelengths, what is really, really an important metric is the speed of the sound. And the speed of the sound is very different in air than it's in water. The water sound speed is usually 5 times faster than in air. And it's actually even faster in really, really solid material like steel, for example, or concrete. That's when you're in a concrete building and somebody is playing loud music and there's no insulation, you will hear the sound very, very good, even further away. The higher sound speed means that there's more sound, including the noise, is received by animals over greater distances again, especially for those lower frequency signals, as I mentioned before. But sound speed is not a static figure. So sometimes sound speed is, as I said, in water, 1,450 meters per second, and other times it can go way into the 1,500 or 1,520. And that's often because the water temperature changes, especially in the summer. The upper part of the water column warms up and the sound speeds further up and gets quicker. So when your receiver, even your hydrophone, is in that upper layer, it receives more sound per time unit than, for example, in the winter when it's colder. So how do we measure sound? We measure sound using a metric that is called decibel, which is a tenth of a bell, named after Alexander Graham Bell. And the reason why we're doing that is it's a relative measure. It's proportional to a reference pressure. Usually pressure is measured in what we call Pascal. But when you look at the sound pressures of different sources, you see that there's a huge range of pressure sources, a huge range in pressure. For example, on the top of that table here, you have the pressure source of a seismic air gun. Seismic air guns are used to profile the sea bottom and below the sea bottom to find oil and gas, for example. And that one has a pressure level of 1 million Pascal. And when you compare that to, let's say, a fin whale at 100 meters, it's supposedly 10 Pascal. Basically, at 1 meter distance at the source, it's more likely about 1,000 Pascal. But you can see there's a huge difference between those pressures, and they would be hard to compare them with the large numbers. So that's how some more intelligent people, way more intelligent than I am, came up with the dB scale and said, okay, so we can actually look at that logarithmically and can say, oh yeah, that can be compared. You can be comparing very quiet sounds with very loud sounds. What is really also important is not to compare necessarily the actual dB values measured in air versus measured in water, because they're not the same. They're not the same because the reference pressure used in air is very different than in water, because air can be compressed much, much more than water. And when air gets compressed, the sound energy can move in all different directions and dissipates much differently than, for example, in water. So don't go and say 120 dB in air. Oh man, it's really 120 dB here. It's really, really loud. It's like a starting jet underwater. But no, that's not really true. It's not the same number. So the two things that Ben also mentioned, he showed you a scale that shows the sound pressure level, which is the very physical measurement of the sound pressure received at a certain area. The other one that we're using is the sound intensity. And the sound intensity is the sound energy that moves through a certain area. And why do we use that one as well? Basically because it is more proportionally adequate for the amount that tissue can take. Like, for example, when you receive certain sound in your ear, in your inner ear, the amount of intensity that goes in here is the amount that the tissue takes on. So that's why we often use the sound intensity as a measure for loudness, for example. So what is important, because it's a logarithmic scale, it doesn't mean that 10 dB is just 10 dB much more than the other number. It means that one sound that is 6 dB louder in terms of sound pressure than the other one, it's actually twice as loud in terms of the sound pressure. And if the sound intensity is 3 dB different, that means it's double the sound intensity. So that's, for example, if you have two sources of sounds and they're 3 dB, when you add them together, you basically get the 3 dB more in your measurement. Now move on to noise and impact. I'll give you a couple of examples of what noise sources would typically find. You know, ship noise, drilling noise, pile driving, commercial sonar, air guns, I already mentioned those, and military sonar. And what we need to know when we want to look at these is, what is the sound level or the sound intensity level that those sources put out? How much sound travels through the environment and what happens to the sound in the environment? And what actually is the receiver able to receive based on what happens, gets to it, but also based on the fact of what the receiver can perceive. What can it hear? What can it perceive in terms of sound? And we often use the frequency and the amplitude and the duration of sound as indicators of how much is actually changing in terms of between the source and the receiver and what the receiver can get. This graph shows you that there's a relationship, of course. The noise source has a certain frequency range, and that frequency range has to be matched by what the animals actually can hear. So on the bottom part, you have the frequency ranges of the noise sources, shipping, seismic surveys, pile driving, oil and gas drilling, but also military sonar, for example, low frequency active sonar and mid-frequency active sonar. They're point sources. That means at a very, very specific frequency, they put out all the energy out there, which is very, very important, because that's why we need the duration measure in terms of what it can be. If there's a very, very loud sound that is just in one frequency or in a couple of frequencies, it can cause a huge amount of damage to the ear, for example, or to the hearing apparatus in total. On the top, these are sort of the average ranges of what we think these different groups of animals can hear. If you were to more interested in what specific kind of animal can hear and can receive, then you would use what is typically called the hearing curve. It's related to what you get when you get a hearing test done, but it's not exactly the same. This is the hearing sensitivity curve for what actually can be potentially received by an animal based on testing many, many animals. In this case, it's not actually that many, but as many as there was possible. But in humans, you find the same kind of curves, and it's tested with millions of people. How do you read this? On the left one, you saw there's these numbers from 0 to 180. Those are dB. That's a dB scale. And on the bottom, you have the frequency. I think Ben showed that as well. It's a logarithmic frequency scale. So it goes from about 100 hertz to 1000 kilohertz, which actually is, in this case, because it's for orcas, it's a little bit over 100 kilohertz that the range ends. And what you have to see here is that the lower the number on the left, or the lower the frequency, the dB level is, the higher the sensitivity is. That means a sound that is only 35 dB can be heard by an orca if it is in a range between, let's say, 20 to 50 kilohertz. And that's an important thing to consider because, as I said earlier, lower frequency sounds travel further, but the hearing might not be as good for the animals in that case. So if you have noise in that area, the masking of that noise can be quite substantial because the hearing is not that good in that part. The second thing that we always consider as well at the same time is that what kind of signals are these animals producing? Orcas, we know, produce communication signals, has a particular range, and you can see where that fits into the hearing scenario, and then where fits the echolocation into that hearing scenario. By the way, if you would, as a human, would look at a hearing curve for humans, it would not go up to 100 kilohertz because, yes, we cannot hear that sound. But that is also related because underwater sound speed is higher, but we won't go into that detail. What is important to see here is that the overall listening space that you have ranges from somewhere between 100 hertz to close to 100 kilohertz. And that's the listening space that is available to the animal. And why is that chosen? Because the 120 is somewhat a typical range that when you compare it to humans, where humans would be hearing not the sounds, but that level, that sound level would be heard. And it's, again, don't use the numbers because you can't compare the numbers to in-air sound. What we typically do is we using a cautionary line. So that means all the frequency, the best tested value or the highest sensitivity will be plotted. But when we're looking at ship noise, which is sort of showing up on top, it's sort of the frequency range of ship, we use a 1/3 octave band, which is a different way of looking at sound. The reason why that is because when you find in literature, ship noise is often presented as 1/3 octave bands. So you have to compare it to the right hearing in order to determine what it is. 1/3 octave band means just like certain sound levels are integrated over a larger frequency band. Again, I already mentioned that. The next thing that we want to know is what are sort of the masking potential of sounds that are produced. In this case, is a scenario where I'll show you a large vessel sound. It's the typical sound of a large vessel is on the bottom right. It shows you what we call the Lloyd's mirror. In the middle at the center is exactly underneath the vessel. That's what the sound is. On the left, on the Y scale, you have the frequency range. In the middle, you have the center, and then you have the dissipation of the sound levels to either side of the vessel. What is important to compare is like where does the most of the energy sit, and how does that overlay or mask, for example, with the communication signals, and which one masks the echolocation signals. And that's a quite good one. For in the center part, you see that echolocations, that the noise levels are really, really high of that one. So they can actually affect the higher frequencies of the echolocation signals as well. Whereas the lower frequencies on both sides of the vessel also overlap or mask the communication signals quite well. It's not just large vessels, as Jackie already had alluded to earlier. Small vessels have the same effect. And what we have to consider when it comes to small vessels is that it's the frequency. And Ben showed you some of the things of when there's an increase in number of vessels per day, you would have to see, well, yeah, if you have 1, 2 large vessels going through, but if you have at least 20 smaller vessels at the same time, you have to look at the duration of how often does that happen, and then gives you an idea of how much actual masking is happening over that course of the day. So that's a very, very important part. What I show you here is you have the killer whale, the orca hearing sensitivity as the sort of beige curve in there, and then the noise level, which stays pretty constant for smaller vessels over a larger range. And then you see the masking potential is highest for the lower frequencies. Again, that means that the listening range of the whales is quite reduced, because the sound has to be louder to be heard by the animal, because the hearing sensitivity is not that high there. I actually summarize quickly. Hearing range and signaling has adapted to changing soundscapes. That's because adaptation is a consequence of what needs to be done biologically, which is the function is survival and reproduction. So as Ben mentioned again in his thing, that was great that you would come before me. That's really helpful. He was pointing out wind noise. He was pointing out rain noise. He was pointing out different types. So these things is part of what's part of the natural soundscape, and the hearing range and the signaling, of course, has adapted to the changes in those soundscapes. What we really are interested is, what type of noise are we going to be putting in, and how does it actually reduce the acoustic quality of the animal habitat, and for what time period? And then for me, and that's my study area in particular, is how much adaptational flexibility exists in marine animals to deal with fast changing acoustic soundscapes. And that's partly related to what we're seeing right now. We have climate change that's affecting water temperatures quite heavily. We know that sound speed is changing due to water temperature changes. Whole acoustic habitats are changing potentially due to climate change, and that of course changes the acoustic quality of the habitat as well. And then if we put our own noises in there, then we don't very quickly, we have to really understand what happens, because potentially the impact can speed up in those areas. So I want to leave you with a sound of a marine mammal, and just to give you an idea that some marine mammals sound very eerie and very interesting in some ways. I will play that to you, and then just to give you an idea of what some of those animals actually sound like. If anybody would have played that to you, not saying what it is, would you have guessed that that's an animal? The first time I heard it, I was not. It is an animal. It's a Weddell seal. It lives in Antarctica, and the reason why it makes these really funky sounds is because it lives in ice all the time, and the ice is in order for the signal to travel in that environment, it needs to come up with some real big strategies to create sounds that are very diverse and have energies in very different frequencies in order to get through to the receiver. So, and that's the end. Thank you for listening.
Thank you so much, Harald. That was wild. And thank you as well, having a sense of just how complicated sound is for bringing across in such a comprehensive way. We have a few questions, and then for real, we have Helena. Talk about how we actually get to have the sound of Helena all the way from OrcaLab. But the quick questions, one of them was asked fairly early on, and I think might allow for a summary, because the question is, how far away can you hear the whales? So how many variables do we have here?
So that's a very good question, because that's part of my job. I'm trying to figure out what are the detection range of vessels of whales from different kind of receiver stations. And to tell you the truth, it really depends. It is not a fixed number. It depends on a lot of things, but primarily it depends on noise. The ambient noise level is the biggest influence on detection range. And in some places here in the Salish Sea in the south, we have sometimes detection range of orca calls that are less than 200 meters. And at other times when it's fairly good, the soundscape is quiet, you can get up to 10 kilometers and sometimes even more. And in the area where you are further up north and where Ben and works, you can get all the way up to 15 kilometers at times in a range. But again, it is really depending not only on the noise, it's depending on the soundscape parameters itself, like propagation conditions that exist. The water temperature plays a big role, all those things influence. So it's not a static one.
Thank you so much. And thank you, Myrna, for that question. A question from Melissa. What is the impact of ocean acidification on whale sound? My understanding is that it reduces the distance that sound can travel.
The acidification changes potentially maybe the salt content, and that could be something that has an effect. But I think the warming part is the bigger issue. The top layer of the water gets warmer and warmer and warmer, and it's on average stays warmer longer. And so that has a huge impact on the sound propagation. And especially since we put in like ship noise into the upper layer of the water, it also increases the chances that increases the sound levels of anthropogenic sound. But the acidification itself is more an effect on, for example, coral reefs, the bleaching part, those things, and the CO2 contents of the actual water. How much actually the oceans are still a sink for carbon dioxide, but with the climate change, it will be less so in the future.
Okay, thank you so much, Harald. There are more questions. We're not ignoring you. We're saving them for the end if they're more holistic, where I think more than one panelist will answer. I am putting Helena on speaker, via WhatsApp, and you can hear her now, can't you?
If I speak, yes. Can you hear me?
Yeah.
Yes, we can.
Great. Okay. Well, I'm going to say good evening, everyone. For over 50 years, listening to the ocean has become a way of life for those living and working at OrcaLab. OrcaLab was established in 1970 by Dr. Paul Spahn and is located on Yucatan Hansen Island, Strait, and Blackfish Sound. It's guided by the philosophy of learning without interference. To that end, OrcaLab developed a remote hydrophone network to monitor the Johnson Strait, Blackfish Sound area. This area has since been designated critical habitat for the northern resident orca community in recognition of its importance to these orcas' historical use of the area. In addition to northern residents, the area is home to a variety of cetaceans, bigs, orcas, dolphins, minke whales, humpback whales, porpoises, and other marine life dependent on their acoustic sensibilities in order to survive and thrive. For us, the use of hydrophones for passive listening has been essential for observing, monitoring, and recording the ocean world beyond our shores 24/7 throughout the entire year. We began with local hydrophones placed just offshore of the lab, and then due to an awareness of increasing boat traffic, experimented with locating hydrophones at strategic sites until we established a remote network consisting of 6 to 8 hydrophones. We routinely monitor approximately 50 square kilometers of the core area listening from east of Naka Creek to Telegraph Cove, including the rubbing beaches along Vancouver Island and Johnson Strait, and from Blackie Pass to Blackfish Sound to west of Donegal Head in Queen Charlotte Strait. Signals from these phones were relayed back to the lab at first via VHF radios and more recently via microwave radios. Although whales and dolphins make incredible sounds and survive by listening, they do so in an ever noisy environment. After honing acoustic abilities as sound producers and expert listeners over thousands of years, their natural world has been rudely intruded upon with the introduction of noisy motorized boats and industrial activities in less than 200 years. A mere blip in time, but one that has had huge consequences. Whales and dolphins have had no choice but to accept this reality. But it is unsure what mechanisms they have used to adapt, if indeed they have. That surprise sharp event, such as the deployment of acoustic harassment devices, naval sonar experiments, and the blasting of seismic air guns caused, at the very least, disturbance that were sudden, painful death. The delicate airwaves used for receiving and producing sound are incapable of dealing adequately with such acute noises. But what of their daily life, everyday lives? Where we live, boat noise is a near constant. And on any given day, tugboats, cruise ships, sports boats, freighters, ferries, pleasure crafts, fishing boats, large and small, might be transiting through, often several sites at any one time. The sonification of the surrounding ocean might occur for miles. A virtual natural sound, subtly penetrating at the near whale or dolphin, needing to locate food, keep yourself safe, and communicate with others in such a noisy environment. By putting loud mechanical noises into the water, we are literally handicapping those that live there. This is what we're talking about. Here's a snapshot of OrcaLab's hydrophone signals. The most visible spectrograms at the top are expanded views of two hydrophones located approximately 6 miles or 9 kilometers apart on the strait. Both show the noise generated by the propulsion system of a large vessel traveling from west to east. The original blue background has become colored almost entirely green-yellow in the presence of such noise. Depending on the speed and type of boat, this kind of event can last from a half hour to 8 hours if it happens to be a log-going tug. So why, you may be asking by now, does anyone listen to hydrophones day and night in the face of such hardship? The answer is simple. Whales and dolphins make incredible sounds, and hydrophones give us windows into lives largely spent below the surface and out of sight. Northern resident orcas have a remarkable social structure where acoustic traditions are passed near seamlessly from mother to offspring. Even while still in the womb, the babies are being imprinted with the calls of their mother. When born, they are primed and ready to understand who they are and where they belong. They will stay within their natal or matrilineal group for the rest of their lives, along with any living siblings, uncles, aunts, and even grandmothers. Each matriline has its own sound or dialect made from a collection of stereotypes. Within the community, matrilines who share a call type in common are unrelated. A higher degree of similarity determines just how closely related. There are currently 44 matrilines in the northern residence. What we've done for discovered that these major lands could be organized into three major acoustic traditions or clans, with each dubbed A, G, and R. Each clan is composed of a pair of these types in common. Between the clans, there are no shared call types, and yet they are one community and interacting with each other would be known to us that had not dropped upon in the water, concentrate and let it nice to keep settled. In County and Gramella. Complex acoustic world of these orcas gave us just the tool we needed as we developed our remote hydrophone network around the same time. Understanding how to identify community gave us the ability to follow their movements, their area. Pretty soon, we were collating and mapping daily a large amount of information from our recordings and any available visual reports. Intricate movements, associations, and social protocols when the orcas were using the area were revealed and illuminated. Our network acted as a large array, capturing and localizing sound within its range. Some days were very busy, some less so. So what is listening to the ocean like on a good
I'm so sorry, Helena. I think it's become really limiting. My voice is not your voice, but because it's broken up so often, I think I'll read your words. Sorry, Helena, did you hear me?
Yeah, I can't. You're breaking up too, Jackie.
Marika will text you here. Helena, I will read for you. Please to everybody, this is so unfortunate that it's happening. I will continue where Helena had left off, having had the foresight to quickly share her words with us. So what is listening to the ocean like on a good day? One August evening comes to mind. Johnston Strait had been busy all day with about 30 orca from various A-clan matrilines going to and fro, traveling to the west to turning, traveling east to the ecological reserve, turning once more, leaving the strait, and heading out past the lab and on into the western sunset. They were not done. They left only to return with even more company. After nightfall, distant at first, their collective calls became stronger and stronger as they drew nearer. Eventually, over 80 orcas from all three A, G, and R clans were in Blackney Pass in front of the lab. The moon was rising over a calm ocean that belied the excited cacophony of sound below the surface. The whales were so excited, their blows everywhere. As they moved slowly through, northern lights began to dance across the sky, as if a complementary mirror to the activity far below. For once, there were no boats, and the whales made their way to the strait undisturbed. Beyond insights as to how orca communities function, their sounds inform us about special behaviors. In the days before we augmented the remote hydrophone network with a complementary remote, we were solely reliant on our listening skills as we monitored the main rubbing beach within the Robson Bight Michael Big Ecological Reserve. Our first clue that the whales had commenced rubbing came when we heard the distinctive sound caused by the displacement of pebbles as their bodies grazed the sea floor. Rubs may last less than a minute or hours and involve just one individual or many from several different families. We have not yet talked about humpback whales. When the humpback started to come back about 2 decades ago, after being decimated by coastal whaling, they were virtually silent. As they became more frequent, perhaps more comfortable with their surroundings, they began to vocalize until they made more sustained efforts and graduated to song. Come autumn, male humpbacks often vocalize throughout the night, super sensitive to the incursion of boat noise on their vocal efforts. They tend, sadly, to fall silent in its presence. We need now to fast forward. After years and years of dutifully monitoring, observing, and recording from our old-style analog hydrophones, it became time to renovate. When OrcaLab started, there were no other such hydrophone networks along the coast. Slowly over time, others took from this model and developed networks of their own. Opportunity came to combine efforts when OrcaLab, over 4 years ago, joined the British Columbia Hydrophone Network, or the BCHN initiative, and this is what Ben has spoken about. Joining 2 other not-for-profits, the North Coast Cetacean Society and the Citrina Island Marine Education Society, along with the Gitgat, Heltsuk, and Kitasoo-Hey-Hey First Nations, effort was made to systemize hydrophone data collection in areas of the North Coast to the Salish Sea. Funded in part by a grant by the Nature Fund of Canada, OrcaLab was able to replace its old hydrophones with calibrated IC Listen hydrophones made by Ocean Sonics, the same hydrophones used in other locations of the British Columbia Hydrophone Network. The range of the OrcaLab network remained approximately the same. Fishery and Oceans collated with the IC Listen installations at all 3 rubbing beaches in Johnstone Strait. Although OrcaLab continued to live monitor and record opportunistically wherever there were whale or dolphin vocalizations, data from the new hydrophones are also collected and stored continually, 24/7. The goal of the BC Hydrophone Network is multifold: to understand the occurrence of whales in all 3 participant locations, assess levels and impacts of ocean noise, make comprehensive comparisons, and inform the public and policymakers alike. The British Columbia Hydrophone Network has launched its new interactive website, Whale Sound. You saw it here first. We have asked Dr. Ben Hendricks to describe for you the website's dashboard, and now we flash back in time because that has already happened. Okay, it is so sad to literally have lost Helena's voice within this. We're going to move to Valeria's presentation. I see that there's other questions that have come in, but what we'll do is have those at the end. There will be time, and many of the questions are those where multiple panelists would have perspectives on the answers. So without further ado, Valeria.
All right. If you can let me know if you see just the awesome. Okay. So I'll try and make mine as brief as I can, so there's time for questions. So glad to be here today. Thank you, Jackie, for inviting me. So what I'm going to do today is, after telling you a little bit more about noise, although everybody beautifully covered most of it, I think, I will spend some time sharing a little bit of my work on beluga whales and noise. Even though we don't have belugas in BC waters, they are sound-centered cetaceans, and what we find out about them is very transferable to other whales. And then I'll go over some of our noise-related Raincoast projects. So noise is really a sound that is unwanted. You have probably all experienced very unpleasant sounds at one point or another. And there's really little doubt that noise pollution above the water is a threat to human well-being and health. We have tons of studies from cities indicating that noise interferes with our sleep, with our ability to concentrate, with our ability to communicate with each other. So it really should be no surprise to us that if it's really that big of a problem to us, it would be a problem for very sound-centered marine mammals. The levels of underwater human-generated noise have really increased tremendously during the last 60 years or so, all over the world's oceans. And chronic exposure to noise causes tremendous stress for whales. Their sense of hearing is like our sense of vision, so navigating in noise is for them, bioacousticians always say this, is like navigating in a sort of acoustic smog or acoustic fog. And whales use sound for nearly every aspect of their lives, and I feel this was very well covered through the presentations we've already seen. So all I will say right now is that noise interferes with all of these activities and causes things like displacement from habitat, decreasing in foraging success. Foraging, it's their ability to catch fish or prey. It can even cause hearing loss and death in some extreme cases. And understanding how noise impacts whales is very much related to the study of cetacean communication. I always enjoy showing this moment that I captured at midnight when I was studying belugas in the Arctic. And to emphasize again that how whales use sound is just a fundamental aspect of their ecology. And when we gain insight into what all these sounds mean and how all these sounds are used, we pave the way to understanding what the potential impacts of noise can be on their ability to communicate effectively. So what you're going to hear next is a little clip that I recorded from beluga whales in 2008. So some of that, you could hear that, right? I hope. Great. So some of that was communication, some of that was echolocation. Belugas are called the sea canaries for a reason. And one of the most important impacts of vessel noise on cetacean communication, and Harald talked a little bit about that, is communication masking, which is basically the reduction of communication space. And communication space is the effective range over which a signal can be detected and decoded by another whale of the same species, bioconspecific. And communication masking can impact the ability to stay in touch with your group if you're a whale, to coordinate your movements. It can interfere with very important social behaviors. And the consequences of communication masking can be particularly adverse in the case of very critical vocalizations that maintain contact between moms and their very dependent but precocious calves. So the St. Lawrence beluga population is the southernmost beluga population. It's geographically isolated. It's declining. It's been considered declared endangered in 2016. There's about 900 animals left. And for a number, since 2006, actually, to be precise, we've been collaborating with the Group for Research and Education in Marine Mammals in Quebec and a number of other partners on various studies that have to do with beluga communication and with impacts of noise. So beluga newborn calves have been dying at an alarming rate since 2008, and also females have been found dead from postpartum complications. And high noise levels and anthropogenic disturbance have been identified amongst the three main threats. The other two threats are prey shortage and contaminants, which these are actually the same three threats that afflict southern resident killer whales here on the West Coast. So our work on beluga communication has informed our ability to understand noise impacts and our work on noise impacts. And I wish I could proceed to tell you all about how belugas communicate, but that would be a whole different talk. So I'll focus on noise today. And I'll just say that we spent 2 summers monitoring ambient noise at Basin Marguerite, which is an area of high residency for female belugas and their calves. And we worked from a research tower. We had a couple of hydrophones in the water. We collected visual information about boats and about distance from those boats to the whales around the tower. We worked from a tower so that we wouldn't disturb them acoustically, so that we wouldn't be one more boat putting noise into the environment. And we also estimated the source level, so the loudness of the contact calls that belugas make to establish and maintain contact with each other. And we did this through D-tags, which are temporary tags that attach to the whales via suction cups, and also from a couple of captive newborn beluga calves. And so this actually allowed us to model the communication space of each call and the degree of masking. This is a representative, just one call. I'm not going to show you the model. I'm just showing you a representative beluga call. The no boat scenario is the median noise level when no boats were present in the bay, and the boats is the median noise level when boats were present. And in the absence of boat noise, most frequency bands between 1 and 10 kilohertz, and as Ben explained, frequency is how high or low a sound is, would be audible to a conspecific between 1 and 3 kilometers away, with the maximum bands being audible at 6 kilometers. And in noise, most frequency bands would be inaudible past 500 meters. So really huge difference with boat noise. And the difference is even more stark for little newborn calves. This is again a representative call, one of many that we recorded to illustrate the potential reduction in range. And the maximum audible distance in the absence of boats would be 300 meters and less than 150 meters in boat noise. So in English, what this means really is that the maximum communication ranges for adults are about 18 times larger than for calves. Beluga calves basically whisper, and newborn beluga calves then are particularly sensitive to increases in noise. And this reduction in range at which their very soft baby calls can be heard by their mother means that if mothers and calves separate for any reason at all, reuniting again can be a lot more difficult in noise. So it's really a dire problem. Next, very exciting project is the project that is very new, just starting, Singing to be Heard. It's another project that has to do with the way cetaceans use sound and with impacts of noise. It is a postdoctoral project led by Dr. Erin Wall, who I hope is listening in from Finn Island. It is a MITEX collaboration between Raincoast, the North Coast Cetacean Society, and the University of Windsor, with really important contributions in terms of stations and hydrophones from OrcaLab and Symonds. And Erin will be doing fieldwork at Finn Island and at OrcaLab starting last week. So we're so grateful for this opportunity. And she is right now listening in from Finn Island, so she'll be happy to answer questions at the end. So just a brief introduction to whale song to better explain this new study. This is probably one of the coolest things about humpback whales, is that they sing these very long, complex, elaborate songs that they learn socially, that are culturally transmitted, and that they gradually evolve year after year. And how this came to be known is a beautiful story. It was the 1950s, during the height of the Cold War, and the military had built a network of underwater hydrophones to track submarines. And so with what sonar operators began to hear amidst the human-made sounds was the songs of the whales. And so in 1968, one of those operators was authorized by the military to give those recordings to a very young and eager whale scientist, whose name was Roger Payne, assisted by researcher Scott McVeigh. And together, Payne and McVeigh published what it really was a pivotal paper that made the first connection between humpback song and bird song. And the story was so good that it appeared on the cover of Science. And there was also an album released by Roger Payne that demonstrated for the first time the elaborate song of humpbacks. And this did a lot to get people interested in whales. At the time, humpback whales were severely hunted. So this album really triggered the Save the Whales movement. So what do we know so far about humpback song, and this is in really a nutshell, is that humpback whale songs typically last 10 to 30 minutes, but they are repeated for hours on end. Roger Payne can often be heard in talks saying that they can sing up to 36 hours without stopping in their breeding grounds. The songs have low frequency components that transmit very far, although the higher frequencies don't transmit as far as the lower frequencies do. Only the males sing, and they sing during mating season, or so we thought. And a little bit more about this in a second. And what makes the song even more fascinating is that its evolution between seasons. And Cathy Payne, who's a bioacoustician, used to be married to Roger Payne, figured out that the songs evolve over time, and that they transform over the years. And there's sections that completely disappear and new themes become incorporated. It's a little bit like art. And this graphic here shows one song traced over a period of 5 years. And the color highlights the changing sequences. So purple and blue units become longer, and then green units are added by the whales. And all the whales within a population change their song together synchronously. So this is a really beautiful example of cultural evolution. And in recent years, there have been a number of studies on cultural transmission of whale song that indicate that humpbacks can learn new songs while they share migratory routes, and that they practice and develop their songs on their feeding grounds. So a lot of this work has come from the East Coast. We know that here on the BC coast, humpbacks sing, and we know that these humpbacks migrate to spend winters in Mexico and Hawaii, but we know very little about the process of song development on the feeding grounds, and to what extent vocal learning is shaped by things like social interactions and vessel noise, which is very prevalent. I was so excited to hear from Finn Island yesterday, from Grace and Erin that are there, that they heard a beautiful song in the morning, and they were so kind to share the song with me. So for the sake of time, I'll stop it there, though I could keep going forever. But the fact that humpbacks practice their songs, that they learn their songs from each other, like this is key. They need to hear each other. They don't sing in a vacuum. They listen to each other. They sing to be heard, is fundamental when we think about what the impacts of underwater noise might be. So in this study, Erin will be analyzing both historical and new recordings from a number of locations along the Pacific Northwest. And she'll be studying song development and practice in humpback whales. And this is a study that is just really close to my heart, and I'm so excited to be working with Erin and Janie on this, and stay tuned for more. Another noise-related project is the Pender Island Interim Sanctuary Monitoring Project. That's a mouthful. Raincoast recently completed the installation of a visual and acoustic monitoring station in an interim sanctuary zone for southern resident killer whales. This is an area where vessel traffic is essentially prohibited from early June till November to reduce the acoustic and physical disturbance on killer whales. And the idea is to increase the likelihood of detecting killer whales and other marine mammals, to monitor and report vessel violations, hopefully to increase compliance. to document underwater noise levels over time to see how well the sanctuary is working, to record humpback whale song for the Singing to be Heard study, and to stream audio and video in real time for public outreach and education. And stay tuned, as we will be sharing the link with everybody very soon. We're just working on some glitches right now. And finally, a project that we've been working towards for the last 4 years is Noise Tracker. It's a collaborative initiative to monitor ocean noise. The initiative is only being jump-started by Raincoast, but all decisions are being made collaboratively. And it is really an effort to provide a logical, very easy entry point for people interested in finding information about noise trends along this coast. And it aims to integrate and present acoustic data from not from new hydrophones, but from any existing hydrophones or networks that are already there, on a very public friendly open access central platform to make it all less fragmented, also directing traffic to other sites that monitor noise to amplify those efforts, such as the BC hydrophone network. That's all I have time to say today about Noise Tracker, so stay tuned again for more developments. And I just want to end this talk on an optimistic note, let's say. There is something that we can do about noise. We simply need to turn down the noise, and that is doable. We can implement ship quieting technology. So we have a concept of zero emission vessels that needs to be redefined to include noise emissions, basically. Things like refits that clean the hull or polish the propeller can reduce noise by 3 to 6 decibels. And remember from Harald's talk that 3 decibels is quite a lot because it's a logarithmic scale. Slowing down ship speed is really reducing ship speed is an effective way to reduce underwater noise. Setting aside quiet sanctuaries or no-go zones, as recently implemented for southern resident killer whales. Of course, and I this is, I think I'm being redundant with number 1 here, incentivize the use of quieter ships. Although by incentivizing, I also mean things like when ports have tiered port fee systems, as done by the Vancouver Fraser Port Authority, where quieter vessels pay lower fees, and that sometimes can work very well. Change shipping lanes to avoid known whale key areas. And what you do is really important. Consumer choices, the majority of shipping is for the transport of goods, really. So buy local products, buy fruits and veggies that are grown in your own country in the right season. Avoid contributing to marine traffic by reducing consumption that is unnecessary. Don't use Amazon as much. And finally, of course, monitoring noise trends to improve efforts to reduce noise. And I think that's it for me. Thank you very much.
Thank you so incredibly much, Valeria. And I think we'll transition right away to the second animation and listening to a humpback and the reality of their world. Wanting to say that we're really, really excited by Erin's study as well. And to think that you've got male Central American, Hawaiian, and Mexican humpbacks in the same waters in the feeding grounds. We can't wait to find out what is learned from that and how they're learning from one another. So folks, we will get to the questions. We wanted to share the second animation with you. Dawn, who is the artist, is, I think it's now 5 a.m. for you, or getting close to that, Dawn. Please, if you've got any questions for our artist as well, add those to the Q&A. But here you have, again, sound made available through the work of OrcaLab, Dawn's skill, and the reality of a male humpback whale in Blackfish Sound. And that is what this is about, is reducing the sound. I'm going to remind you already about the Ocean Voices website. We'll be adding a edited version of this, the recording of this webinar on there. It has links as well to Noise Tracker and to the fantastic resource that has been announced today as well. So to move through the questions, one of them, Ben, and please, other panelists, let me know if you also have input, but I think this one might be specifically for you, Ben. It's from Jill. I'm pretty sure that artists working with scientists is our only hope. I'm a sound artist, developing ideas. We're using public sound art to raise awareness around the acoustic worlds of marine mammals and the impacts of anthropogenic sound. If an artist wanted to access an archive of Salish Sea hydrophone recordings, where would they start, Ben?
Yes, that is an excellent question, because it is a topic that I think is currently milling throughout the community, how to make that possible. It's many different organizations that are involved with collecting data, and then you have a combination between the technical aspects of getting this data prepared and other decisions where and how to make it available. And I think, to answer your question, at the moment, your best bet is to find out the email addresses of the organizations who collect data and write them that you would be very interested in that data. And if we get enough of these emails, then we have enough incentive to push these projects forward. Because I'm also a big advocate for creating a platform for these types of products that are not just for a scientific purpose, but also for people to actually connect with that world and with the beauty of it.
Hey, brilliant. And on that note, there's an enthusiastic note from Darla. I love this stuff, and it gets me so excited. That's Darla's voice. Yeah, I have some great recordings from the Prince Rupert area from last week. If any of the experts here are interested, duly noted, Darla. Thank you very much. The next one, I think, starts with Harald as answer. It's from Youssef. I'm a sustainable leisure management master student. I'm studying how electric boats can be a sustainable solution to whale watching tour operators in Vancouver Island because they are soundless and non-toxic. There was a lot of research in Iceland and Norway that is very successful from the data I collected. So please, about electric boats, their promise and concerns.
Well, it's a good question. Very good question. Yes, there is the change, for example, especially with the engine noise and the propagation of the engine noise is correct. There's less noise that comes out. It still has noise from the actual axle and the prop and other things that are still producing noise. But it is a huge change, and as far as I know, I think both of the major ferry corporations want to change. They're trying to get money to change their fleets around to at least go to hybrid vessels, and eventually, potentially, at least in Washington, going to full electric ones. And yes, it is. It will make a difference. It will make quite a bit of a difference. But yeah, it won't eliminate the noise completely.
Which I would suggest is a good thing, because we don't know how much the whales rely.
That's a good point. That's a good point, Jackie. Especially when, with small vessels as well, stopping and having no noise at all. Also, it sometimes means that the whale don't know where the vessel is, which is potentially risky for the whales itself.
And I don't know if any other panelists have an addition to that. No,
that was great. Yeah.
Thank you so much. So Myrna's question follows up on this. Are there any theories to explain why whales don't seem to recognize ferry noise? And it's not, of course, just ferry noise. It is boat noise. And I think we're talking baleen whales here. And why they don't always seem to avoid routes that ferries usually take. I understand that they need to feed and travel in these same areas, but I'm curious if they understand the dangers of ships.
maybe I jump in there. Oh,
Yeah.
Valeria, you want to go ahead first? That's
No,
cool.
no.
No,
Yeah.
there's a lot of theories around that, obviously, but yes, first of all, the main reason is they have to be where the food is. That's one of the big reasons. They can't just move anywhere else, and that's the whole part of thing. Why don't whales move out of area that are noisy? Because they literally have to make a living, and they have to be there. The other part that I think is also important, many of these larger whales, many of these large baleen whales, from their development, from their evolutionary history, they were pretty much the biggest things around. That was always around. A blue whale was a biggest animal. If the blue whale itself has any interaction with a large vessel as an individual, how would that information that a large vessel is actually dangerous to them be implemented in their memory? Because it's not part of their upbringing, it's not part of their existence by itself. They have to actually make contact with the vessel itself sometimes. And yeah, there's social learning. They may learn from their parents, but yeah, no, they may actually be just simply not aware of the danger of these vessels.
That appears to be the case.
Mhm.
Thank you. Does anybody else have follow-up to that?
It just that it reminds me of very often people ask the same question of animals crossing highways and being killed. Why do they continue to be killed? And it tends to not be something that can be sort of imprinted on an evolutionary scale or learned socially. You're dead, and often you're dead alone and nobody watched, and you don't pass on that information. You don't have an encounter with a predator and survive to learn from it. You're dead. You don't pass on the story, so anyway.
I think to add to that is I think it's so important to realize just the intensity of what baleen whales are doing. They have to get fat so fast in these waters because they will spend so much time away to where there's little to no food for them. And part of what the boater survey that we're doing is revealing is that around 40% of boaters believe that they go to warm water to feed. So like from a small vessel understanding, or even how we're impacting large vessel traffic, there's an abject lack of understanding, big opportunity there for understanding that's what they're doing here, is that they are feeding here. And as a result, yeah, they are going to be potentially even more oblivious, except that mating is really important too. Okay, this one, COVID. Of course, we wanted to talk about that. Yeah, it was going to come up. Can you explain how you've been able to use the 2 years of reduced noise from COVID's reduction in at least cruise ship traffic? I'm glad that was said, because we sure didn't stop buying things on Amazon and driving vessels around the planet, or how other smaller boats offset benefits of reduced cruise ship traffic. How you've been able to integrate the perceived anthropause from COVID into your research. I can speak to our colleagues' research in Alaska if that's of use at all, but anybody in how that's, I don't know, Ben, with the archived hydrophone recordings that might allow for somebody to look into that more concretely in the future?
Yeah, it's generally an important aspect to look into, and the reason for this is that we're not yet often in the position to actually know what a healthy ocean looks like, just because we're just starting to put these hydrophones in the water, and we're just starting to get a baseline of what a ocean look like, and we do not know if that's normal, if that's healthy, or if it's already on some level of concern for ocean health. And having that data available is, I think, a unique and great feature. Specifically for the BC Hydrophone Network, a lot of sites have just been established around that time. So in that respect, it hasn't been ideal that that the technology all came together around these years, because we haven't been monitoring for years before and could see a certain change. But I think organizations like NCCS and OrcaLab, who have their eyes and ears on the whales for many, many years, they have documented changes and patterns that are for sure available.
Yeah, and to that, the humpback whale research colleagues in Southeast Alaska who have such extensive data sets, they were able to notice that in the absence of cruise ships, because there's a lot of cruise ships that do go to Southeast Alaska, Glacier Bay, that there were difference in the humpback calls. But then you're left with, well, but what do those differences mean? So we do have that as one of the papers on the website. What is also, what we'll add there as well, is there was also research done when the world totally went quiet, and that was during 9/11. So there is research on the East Coast, and I'll dig up that paper and add it for that there were acute differences noted in how the whales were communicating during what was truly a quiet period. I don't know if anybody has anything to add.
So yeah, there's I will probably be published pretty soon. There is spearheaded by Parks Canada and Haida Gwaii. They have several recorders in similar areas where they actually could see that the change in sound, particularly in the noise signature during times when the cruise ships were not there, and they're trying to compare that to the amount of fin whale calls, for example, that were detectable during that time. And you can make correlations between the detectability of calls, especially in large ocean areas when the noise goes down. So, and that of course can be translated to the fact that, well, if we can hear them and we can record them, the whales actually can hear them as well, you know. So the distance over which they can actually communicate improves as a result of that. On the other hand, there is a little bit of an issue with the covert part in the Salish Sea, because we actually had in some places more small vessel traffic during that time, you know. So that is the opposite effect, because a lot of people went, oh, we can't socialize, we can't go to the movie theater, well, let's go on the boat and go fishing, you know, something. So there was a lot more vessels out there.
Okay, super. From Vienna, thanks for the wonderful sharings. My question is, will slowing down the vessel lower the frequency of boat noise and make the sound go further? Tag, you're it, Harald.
Wonderful question. Love it. Well, Valeria has actually something to say to that as well. Yeah, slowdown have been practiced in, at least in Boundary Pass in the Cetacean and in Harald Strait. It has also been looked at on one area in the shipping lane off Swiftsure Bank. It had an effect, 1 to 3 decibel reduction overall on broadband in most in Harald and in Boundary Pass. So there was definitely an increase. There was just definitely a quieting of the area. It did not show up as much in areas such as Swiftsure Bank. And one of the reasons could be because there's so much other ambient noise at the same time, due to small vessel traffic traveling around in the area, fishing activities, etc., that the overall slowdown of the large vessels did not actually achieve that reduction that we would have wanted to see, actually, but it did not happen. There's work now done to see whether specific areas that are important, and that's the other part. When it comes to the slowdown part, and Valeria mentioned that quite well, there's certain areas that are potentially more important for some whale species because it's an active feeding area. It's an area where they often socialize, where they often get together. So if slowing down in certain areas has an effect on specific habitats by actually reducing the noise in those important habitat areas, then there's another positive effect from the slowdown, not the overall reduction in noise, but the specific location-specific noise reduction.
Okay, super. Just going to get one quick one done here. I've noticed for some time, this is from Deb's that BC ferries are speeding up when behind schedule. The staff complain as well. It makes the ships vibrate more. Who do the staff or public report to? They have a system in BC ferries. They have an environmental officer that they can report to. And all the BC ferries going into Vancouver Harbour are part of the ECHO program. So it could also be an issue that's relayed to the ECHO program. I don't know if anybody has anything to add, but BC Ferries is striving to be a leader in making accidents count and have practices to reduce noise and collision. Okay, from Brett, I'm interested in using hydrophone data to train machine learning models for various cetacean tasks. What efforts are underway to archive data with open access licenses?
I think that's Ben.
Well, it's a tricky question. It's very similar to the sound or the song that may become available. I think it eventually boils down to the hydrophone data owners at this point, and something that I think needs to be recognized with, after all the talk we've done about what great things can be done with acoustic data, is it is a lot of money and effort to get the hydrophones in the water and to get the data out. So I think it's not as, unfortunately, as simple as saying, here's the data and now it's freely available for the world. There's it has to do a lot with grants that become available for these projects and how they're used and what the mandates are. And I think very similar to people who like to access, whale song or orca vocalizations. I think the easiest is to start contacting the data owners with these requests, which may be granted directly, or it generates a bigger incentive to actually answer that questions among these groups and see how that can be facilitated.
Thank you so much, Ben. There's a number of questions that are along the same line of, can't boats make noise to alert the whales? Who would like to go there? About the concerns around that, if there's been anything that's proven to be successful.
I'm not sure that is a concern. I mean, it's detectability. Like if you can detect the vessel, yes, it has a positive effect, but detectability can, for a whale and for a dolphin, doesn't need to have high volume or high amplitude. It is a very, very low amplitude sound. So it even a boat in idling mode, even a boat that is there, even potentially even in some places, just the wave action against the boat probably is enough to alert whales of the presence of vessels. So I don't think you need an active sound to make sure that the whales and the dolphins know that the boat is there, and the active loud sound, for example.
Yeah, so I think important here too is like tooth cetaceans have echolocation, so they've got a way that they can detect vessels. Baleen cetaceans are not known to have echolocation in the same way, whereby, but again, tied in with questions of how oblivious they can be of vessels for whatever reason. And I think, sorry, my reference to concerns is what you mentioned. It doesn't need to be active, right? We often get questions as educators is, can't we sound an alarm underwater, where that alarm is then going to add to the stress and you're going to get habituation.
I totally agree.
Yeah.
So, I mean, that's a big point. It's like active acoustics is always a form of, noise pollution. It doesn't really matter, what it is used for. It does have the same effect. So if we can avoid it, then we should avoid it.
Brilliant. There's more questions than we have time for. We are going to hold to 9 o'clock as when we stop. We're very close to that. So forgive if we haven't had a chance to answer your questions. You can email us and we can forward them as appropriate. But one from Katie is, would a toroidal propellers, forgive the mispronunciation, be a good and fast way to reduce noise on existing vessels?
if they are the ones that have been inspired on cetacean, flukes and such, I would love to try them. I know that there are companies that are making them, and I think they are a lot quieter. We've certainly been discussing them at Raincoast.
There's so much potential for improvement, and yes, we are going to end on that note. Yeah, there is so much potential, because this is at the core of all of this, and why the efforts have been put in by Helena and Harald and Valeria and Ben is, if there is an awakening to just how much noise there is and how we're impacting it and how it impacts the animals, there's a lot of ignorance there amongst the general public before now. And the reason we've done this as educators is because with that knowledge, there is then voter power, there's consumer power, and that we can shift things, like if people care enough about how much noise vessels have, including our own vessels, that we can adapt our practices and stimulate technologies. So in that regard, we'll do a round of everybody here. There's a question from Jacqueline. What type of policies need to be implemented to improve the soundscape in British Columbia?
I think we've gone through that. You probably asked that before my last slide, I bet. When I talked about, everything from reducing speed to quiet sanctuaries to what else did he talk about? To incentivizing the quietest ships from ports, so that they get to pay less fees, so that there's an incentive for ships to become quieter. Yeah, even retrofitting the hulls and the propellers, changing the kind of propeller you have. There's so many options. Some of them are expensive. Think of submarines. They're very quiet. The technology to have a quiet displacement exists. It's just it's just a matter of education and adopting those technologies.
What Valeria just said, just to add something, there is a paper that sort of pointed to the fact that for the larger vessel classes, that potentially is 10% of the fleet.
Yeah,
some of those areas that are producing 90% of the noise. So, and that's mostly older vessels, mostly not well maintained vessels. And yes, and there's an issue, for example, some of them, that money is an issue. People don't have the financial means to maintain their vessels to the standard that they should be maintained, and that's a problem. Can that be done by policy? Yes, potentially can be, and Transport Canada is the one that should implement those things. But it's also, like Valeria said, incentives are important. Like, for example, retrofitting incentives might be a good thing to have. And that's something that could be useful.
Hey, everybody, right on 9 o'clock. Thank you, everyone. Thank you, Dawn, that you were here and all the work that you've put into this. Thank you, everybody, for weathering OrcaLab having the hard time of getting through as the acoustic experts they are. Thank you to all the effort that's been put into the website content from our advisors, and a huge thanks to you all for making it feel really worthwhile. Thank you.
Thanks.
Thank you so much.
Yeah.
Thank you, Jackie.
Pleasure to be here. Bye-bye.
Keep well, everybody.
Bye.